Okay, so welcome to this second lecture on geostatistics. In the first lecture, we introduced the realm of geostatistics, which has basically three applications. That's optimal interpolation, the estimation of the conditional probability density function at a given location, given that we know the values at observed locations around it, and the simulation simulating realisations from the conditional random function, given the observation values at the observation points. We introduced two types of kriging: simple kriging, which was invented by Dani Kriege, and ordinary kriging, which is a more relaxed form of kriging that assumes not wide-sense stationary, but can also be applied under the assumption of an intrinsic random function. So the variogram doesn't have to reach a sill, and it can also be applied if you don't know the mean beforehand. And ordinary kriging, as we saw, was the preferred method because it is a little more conservative with regard to uncertainty, because it assumes that it doesn't assume that we know the mean exactly. It re-estimates the mean every kriging interpolation that is done within a certain search radius. It can deal with a larger class of semivariograms, and it implicitly accounts or corrects for trends in the data, even though you assume that the mean is constant everywhere. So it's more robust against the underlying assumptions. So in this particular second part, we will mostly focus on the conditional, estimating the conditional probability distribution function, and also with conditional simulation. Before we do that, I just want to introduce shortly what is called block kriging, because this is actually the original type of predictor that was actually simple block kriging was the original method that was invented by Dani Kriege. And what I show here are the equations for block kriging. So what is the problem at hand here? Suppose we have a certain area that can be a square block, but it can be an area of any size. And there are observations taken outside this area and maybe a few within. Then the idea is to estimate the area or block average value of a property, maybe the average lead content or the average groundwater level or the average hydraulic conductivity. Now, the thing is that this can even work if we don't have any observations inside the area itself. So it's an extrapolation. If you know something about the spatial correlation, you know the values around it, then it may be possible to estimate the value within the block or within the area. The predictor looks the same exactly. It's a weighted average of the observation values in and around the block. And these are the so-called normal equations or kriging equations. They look almost the same as for ordinary kriging, except that on the right-hand side there's the so-called block point semivariance, and that is calculated from the semivariograph by taking the semivariance values between a number of points within the block and the location. So the block is discretized to say with 9 or 16 or 20 or 50 different points, and for every point we take the point semivariance, and then we average that. That gives us an estimate of the average semivariance between the observation point and any point within the block. That's on the right-hand side here. This condition is added to assure that we have a unbiased predictor. And of course, because we add an equation, we also have to add an unknown. This is the Lagrange multiplier, which again signifies the uncertainty about the unknown mean. And then if we calculate the kriging variance, it is actually, it looks the same as for ordinary kriging, except that we have to reduce the total variance with the within block variance. And the within block variance is calculated by taking the semivariances between all the pairs of points of a discretized of points within the block. So this with this, this with this, this with that, and so on. So all the combinations, and then average that. This is an estimate of the variance within the block. Yeah. So you can also see this one becomes larger if the block becomes larger. So if the block becomes larger, the prediction error variance becomes smaller, which is logical because it's easier to estimate the value from a the average value of a very large area, given the information that you have, than for a point. So there's a trade-off between resolution and accuracy, which you always see in many of the stochastic applications, which is intuitively correct. If we increase the resolution and we don't increase the amount of observation, so the information content remains the same, then the accuracy of the predictions becomes lower. Yeah, so the prediction error larger. So you can remember that accuracy and resolution, there's always a trade-off between the two. So this is an example of block kriging. These are the block kriging predictions. So now we not predicting at a grid of points, of 50 points, but we have 10 by 10 blocks here in this case. So every block is 5 by 5 in size. And you can also see that if you compare this is the same scale that we used for the prediction error variance as before. You can see that generally they are much lower because we are now predicting averages of blocks. Okay, so after block kriging, we go back to the other two. This is again a picture of the focus of geostatistics. Remember, we looked at kriging. So these are 4 realisations of the conditional random function, given that we have 4 observations available. And the dashed line here is the average of that, which is the, if it's a Gaussian, multi-Gaussian random function, is the conditional mean. And what kriging can do is directly predict this value of estimate this conditional mean, and that's the optimal prediction of the unknown value, which is any of those realisations. And we can also get the prediction error variance with kriging. Now in the next step we're going to look at this particular part. Given we're going to look at a certain location X, and we want to know how can we calculate, if we know some properties that have to do with stationarity and Gaussianity of the underlying multivariate probability density function. If we assume that, we can actually calculate the conditional probability density at any location. So that's the probability that Z gets any range of values, given that we know the values at the observation points. Now, when we calculate this conditional probability, essentially, so this is how it is stated mathematically. This is the probability that Z is smaller or equal to at x naught, smaller or equal to a certain value, given that we know the values at the observation points. In this case, n observation points. Now, to calculate this function, because it's a function of Z, this is the cumulative conditional probability distribution function. To calculate that thing, there are essentially 3 ways of doing that. One that we are going to treat today, and in this course, is multi-Gaussian kriging. But there are more advanced methods, indicator kriging and disjunctive kriging. Multi-Gaussian kriging is used if you can assume that Z is not only a stationary random function, strict stationary random function Zx, but it also has a multivariate probability density function. This means that it is sufficient to estimate that to assume that the underlying random function is wide sense stationary, right? Because if it's wide sense stationary and multi-Gaussian, it is by definition also strict stationary. That's the one that we're going to look at today. There are two other ways that can be used in case there is the underlying multivariate, even if the underlying multivariate or even univariate probability density function is non-Gaussian. So if you have then you can use indicator kriging or disjunctive kriging. I just mentioned them here, but you have to go to more advanced textbooks to see how this works. Okay, let's go to multi-Gaussian kriging. Multi-Gaussian kriging, like I said, has some heavy assumptions. We have to assume that Z is wide sense stationary and that any set of values are jointly Gaussian distributed. Now I say or their transform, because of course usually many of the geophysical variables that we know are strictly positively valued. Think about concentration, think about soil moisture, think about hydraulic conductivity, porosity. They're never negative. So a Gaussian probability distribution is not a very good model to describe their uncertainty. So what to do? Well, what we typically do is we transform. And I will show you there are many ways to transform. For instance, in our exercise in the practical with R, we use a simple parametric transform, like we take the logarithm of Z or the square root and check whether it's sufficiently Gaussian, and then assume that the random function is wide sense stationary and multi-Gaussian, and go ahead and do the kriging with it. But there's also a more general transformation that makes use of the data. This is called a normal score transform. And what you do is this is your original cumulative probability distribution function, estimated by either by declustering or by if the data are sufficiently evenly distributed across the space, you can plot the value against the rank number divided by the number of observations plus 1, and you get the cumulative frequency distribution. And then basically we transform, we project the rank order and the cumulative probability to a value of a standard Gaussian variable with the same cumulative probability. Yeah. So the probability that Z is smaller than this particular value here, which is 7, is equal to say 0.3. Then we look at the 0.3 quantile of the standard normal distribution, yeah? And then we attach that particular value to it. So if you do that, you make sure that after transformation, our observations follow nicely a standard normal distribution with a mean of 0 and a standard deviation of 1. So what we do is we do the kriging on the transformed, we do the estimation of the conditional distribution on the transformed variable instead of the original variable. Now this transformation, you can do it graphically like I showed here, but obviously it's easy to do that in R. For instance, you want to play around with the auxiliary information. There's an R script called field normal score, where you can see the original Z field and then a transformation of that. You can see this is between 0 and 1, and this one, or this is a strictly positive variable, and after transformation it is between say it's a standard normal one between -3 and 3. Yeah? Here you can see the histogram of this field, and this is the histogram which is positively skewed, as you can see, like hydraulic conductivity would for instance be, and this is the transformed one which is nicely standard Gaussian. Yeah. So if we do multi-Gaussian kriging step by step, it works like in the following. Yeah. So the first step is to transform the data like this. Yeah. Take a normal score transformation. That's the first step. Then with the transformed data, let's call these transformed data Y, and then NS stands for normal is a normal transform of Z. Yeah. Then with the transformed data Y, we estimate the semivariograms. And we fit a smooth function, a spherical model or an exponential model or a Gaussian model through it. Most likely a spherical model fits best. You have to make sure, by the way, that the semivariograph has a sill, because after all, our assumption is that the underlying random function is wide-sense stationary. So no matter what the variogram looks like, in the end we have to have a sill. Now in this case, actually the sill has to be close to 1, because after transformation, this is a standard normal variable, so we know that it should have a mean of 0 and a variance of 1. And therefore the sill is in a wide-sense stationary random function, the sill of the variogram is equal to the variance. So and the variance is 1, so the sill should be 1 as well. So you have to fit a variogram model with a sill of 1. Then you do simple kriging. Why simple kriging? Well, we know that the mean is 0, so we know the mean. It's wide-sense stationary, so the best method to use now is simple kriging. This gives you a simple kriging prediction and the kriging error variance. Yeah. Now, if the underlying multivariate probability distribution is Gaussian, as we assume, and it's a stationary random function, we know that the conditional distribution at any point is given by a Gaussian as well, with the mean equal to the prediction, kriging prediction, and the variance equal to the kriging prediction variance. That's what we can derive, actually. Yeah. Well, you just have to take my word for it, but that's under these assumptions, the conditional distribution at any point is a Gaussian, with this is its mean and this is its variance. So if this is a Gaussian, then we can get this is the probability. We can calculate the probability that Z is smaller or equal to a given value by transforming this value also, Z, with the same normal transform that we had. So we get the normal transform, then subtracting the mean and dividing by the standard deviation, which this comes from the kriging prediction, this comes from the kriging error, prediction error variance. And then we know that we can calculate chi, which is a standard, which is the standard normal Gaussian variable. We can calculate this probability like this, and we did this before. We can read this from a table. The table is in chapter 3. So this is how we can get for any value of Z, first transforming it, and then injecting it into this equation here. We can get the probability that the unknown value at location x0 is smaller than Z. If we do that for multiple values of Z, we can reconstruct the complete conditional cumulative probability distribution function. Okay, we'll show you how this works with the Walker Lake dataset in a minute. But before we go there, it's good to say that apart from the idea that we can now calculate the conditional probability distribution at any point in space. It has and that, why would you want to have the conditional probability distribution? Obviously, because if you're interested in extreme values, you may want to, and you have a certain critical threshold, you can then calculate what is the probability that the value at this unvisited location exceeds that critical threshold. Yeah. Now, apart from the purpose of getting this conditional probability distribution, there are two other reasons why one would choose to use the normal score transform. First of all, it turns out that if you do the transform, you stabilize the variance a little bit, and because you have now you now have a symmetrical distribution and not this long tail distribution, the estimates of the semivariograph are much better behaved. So it's much easier to estimate the semivariograph of a transformed variable. And because sometimes it's used to make sure that the values are within a given range. For instance, if you do kriging directly, so it's not so also in kriging it's often used. For instance, if we want to krig hydraulic conductivity, so point kriging with ordinary kriging, for instance, then if we don't transform, then it is possible that we can predict at certain locations negative conductivities. And there's no condition in the kriging system that makes sure that you cannot have negative predictions. Of course, it makes sure that you cannot have negative variances, but the predictions can still be negative. Or porosity needs to be between 0 and 1. So to enforce that, you can first do a transformation, then do a kriging on the transformed variable, and then transform it back, the kriging predictions. And if you do that, then you make sure that your predicted values are within the range that they should be. So in practice, transformation is more often done than not. Now let's see how this works out on the Walker Lake dataset. So this is the original histogram of the Walker Lake from our 140 observations, and we, as you can see, we used a declustering here to calculate it, because you see the mean is the estimated mean is 2.53. It's not the overestimated mean, and you can see it's extremely skewed with a very few very high variables. So this is very far from Gaussian. After the normal score transformation, you can see it looks like this. Obviously, it's not a very nice smooth Gaussian, but it has to do with the fact that we only use 140 observations. So this is the first step. Then we use the transformed variables to calculate a semivariograph. And that is done here. You can see here, this is a very old program, by the way, that we're not going to use anymore to estimate. So these are the experimental semivariances of the transformed variable, and you can see they're much more nicely behaved than in the original, which was more like this, right? And then we fitted this spherical here. It has a nugget and it has a nugget. In this case, in the initially there's a nugget of 0.2, a range of close to 17, and a CIL of equal to 1.3. Well, remember that we need the CIL to be equal to 1 because it's a standard normal, but after transformation the random function is standard normal. So it means that we need to rescale this thing. So what we did is we rescaled the CIL to 1 and proportionally rescaled the nugget, so that if we add up the nugget and the CIL, the nugget and the nugget, the sill minus the nugget plus the nugget variance, we end up with a sill of equal to 1. So these are the parameters of the rescaled semivariogram: a nugget of 0.14, a sill of equal to 1, so the nugget minus sill is 0.86, and a range of 16.9. So with these three parameters in our kriging program, we are inserted in the kriging program, we can do a simple kriging prediction of the standard of the Gaussian transformed variable and the simple kriging variance. Now, once we have these two fields, we can then calculate exceedance probabilities. For instance, suppose that we are mapping lead content, and there's a critical lead content of in milligram per cubic meters, for instance, and the lead content, critical lead content is 10 milligrams per cubic meter. So what we do is we insert 10 in the normal score transform. So we get a normal transform of 10, and that ends up with a value of 1.5757. Then this gives me the probability that Z is smaller or equal than 10. So 1 minus that probability is the probability that it's larger than 10, right? So I can calculate this guy here with the kriging prediction of every location and the standard deviation of the kriging error. Yeah. And if we have that, we can then calculate for every location, we can calculate the exceedance probabilities. And then you can see those, and there where the exceedance probabilities are very large, those are typically the locations where we would remediate the soil. And here we don't have to do any excavation of the soil and treat it, because we know that the exceedance probabilities are extremely low. Yeah? So this is a very effective way to include risk in, for instance, soil remediation. Okay, so this is the part of conditional estimating the exceedance probability. Let's go to simulation. So simulating realizations of the conditional random function. So what we now want to do is get these individual realizations. Yeah? And there's two types of realizations of the conditional function, of what we can simulate. We can do conditional simulation, where we draw realizations from the conditional random function, or we can do unconditional simulation, where we draw realizations from the unconditional. Yeah, we know that this random function is no longer stationary. This one, of course, is stationary. Now, why would we do this conditional simulation? Well, imagine that we want to take, we have observations of hydraulic conductivity at our 140 locations, and we want to put that into a groundwater model. So we do a block kriging maybe at very small blocks here, and we get, or point kriging, and we get the hydraulic conductivities from ordinary kriging, like here. Yeah. And we put them then into the groundwater model. Now, this is a simulated realization of the underlying conditional random function. Now, what is striking, first of all, we see the high and the low values at the same locations. And that is due to the fact that we use conditional. They're both conditioned on the same observations, right? So if there are more than average number of highly valued observations here, you can see that this is reflected in the simulated field, but also in the interpolated field. But what's also obvious is that this is much smoother than this, and this is actually a better realization, or a better portrayal of the underlying reality, because our reality is just one of those unknown realisations. So reality is very rugged and noisy, whereas the kriging prediction is very smooth, because after all, a kriging prediction is something like a mean of all those possible realisations, right? Which is the dashed line in the previous figure. So this one is actually much too smooth because it's actually the mean. So you underestimate the variability in hydraulic conductivity. So it's better to use this one. Also, and that's not the case here, the degree of smoothness in this particular field depends on where the observations are. If you are far away from the measurement locations, what happens is that the predictions refer to a very smooth, flat surface equal to the mean, the a priori mean of the random function. So, and where you have multiple observations, clustered observations, it's going to be more variable. So the variability of your hydraulic conductivity and therefore of your groundwater flow is determined by where your observations are. Well, this is a property that you don't want in groundwater modeling. You don't want the flow fields to reflect where your observations are. You want to have the smoothness of your hydraulic conductivity to be equal across the field. So this is what I always would choose. I would always simulate a realisation of hydraulic conductivity and put that into my groundwater model. Well, this can be put more general. If you think in GIS type of terms, in GIS you have so-called point operations. So this is the idea. Okay, suppose that we have some model y, which is a nonlinear function of an input z, and z is our can be hydraulic conductivity, for instance, and y can be some output. Well, if this is a point operation, suppose that this is infiltration rate, for instance, this is the infiltration capacity at a location, or infiltration rate at a certain location, that depends only on the hydraulic conductivity of the topsoil at that location. So this is a so-called point operation that maps hydraulic conductivity at a location to infiltration rate at that location. So the outcome of y doesn't depend on any of the locations around y. Only at what happens only of z at x naught. Yeah. So these so-called point operations, then we can use kriging as input, or if we want to include uncertainty, a conditional probability distribution. If we have a neighborhood operation, so if, for instance, the hydraulic head at x naught not only depends on the hydraulic conductivity at that specific location, but also the hydraulic conductivities around that location, because after all there is lateral flow going on in a groundwater body. So with these neighborhood operations, and that includes partial differential equations such as the groundwater equation, then if y depends on multiple locations, we have to revert to conditional simulation. So that's the general rule. Now, of course, this is but one realization of the conditional random function. So we can, of course, simulate hundreds or thousands of those. So which one do we choose? Which of those realizations do we put into our groundwater model? Well, the answer is as many as we can and as many as possible. And then we come to this specific scheme, which is called Monte Carlo simulation. So let me go through it. So instead of one realization, we're analyzing many of those realizations. And they're all equally likely portrayals of our unknown reality, given that we know the values at certain locations. So suppose that this is the unknown reality, the unknown variation of hydraulic conductivity, and we sample it. We have bore logs at 1, 2, 3, 4, 5, 6, 7, 8, 9 locations here, or yeah. So we have n. In this case, we have n different observations of hydraulic conductivity. So from this we can get the semivariograph, the mean, and so on. So we get the statistics. of the underlying of the hydraulic conductivity, and then assuming that maybe after transformation, assuming that the underlying random function is multi-Gaussian and stationary, we only need the semivariograph and the mean, or the semivariograph, sorry, to and the a priori mean of the transformed variable to simulate realisations. How this is done will be shown in the next. But given the statistics of the underlying random function and the values at the observation locations, we can devise an algorithm that simulates alternative realisations of the reality, and they all have in common that they exactly reproduce the hydraulic conductivity at those locations, and that they have the same statistics as we find in the data, the same statistical properties. So therefore we cannot discard any of them. Any of those are equally likely realisations of our unknown reality, given that we know that unknown reality at a number of locations. Yeah. So suppose we have 100 of them, m is 100, we run the groundwater model 100 times. For instance, if we have, we want to see what the effect is on the drawdown in some nature area that's positioned here, for instance, subject to a pumping well in the middle of the domain. So we basically do this, we repeat this groundwater simulation 100 times. So we get 100 drawdown, hydraulic or groundwater level drawdown fields. So for any unknown location, we can then get a probability distribution of drawdown. Yeah. This is, so y is in this case the output head, so we can get the probability distribution of drawdown. Just by taking at any location, we have 100 values and we can compute the histogram of that, or the cumulative probability or the cumulative frequency distribution as an estimate of the cumulative probability distribution. So this is called Monte Carlo analysis. Yeah? So we can also make maps, for instance, the mean drawdown in this case, and the variance of the drawdown at every location. Yeah. So this is how conditional simulation is used in practice. Now this is part of what we call stochastic forward modeling, and we will come back to this in chapter 8, which is all about this. And in this context, we use geostatistical conditional simulation. Now, the last 10 minutes of this lecture will be to show you how this works. Well, there are many different ways to do conditional simulation. In the 1980s, it was actually only possible to do, early 1980s, to do unconditional simulation, and then conditioning was done by a post-kriging step. And unconditional simulation was done with different type of methods that took a lot of time a lot of calculation time. Examples are the turning bends method, for instance, or Cholesky decomposition simulation, nearest neighbor simulation. There are a number of those simulations methods that are were all done that work okay, but they are either computationally demanding or very difficult to comprehend. Until in the 1990s, in Stanford, they came up with a very elegant, simple method, which is called sequential simulation, that by construction simulates realisations of the conditional random function. And it can also be used for unconditional simulation. And this is actually the simulation algorithm of choice. Now, how does it work? Now, what we do here is we assume, what we see here is we see an area, and we want to simulate values at these grid points. Yeah. And these are the observations, locations where we have observations of the unknown variable. Yeah. Now we have to make some assumptions. For instance, after transformation, suppose this is hydraulic conductivity. We've done the transform of the data, either with a normal score transform or taking the logarithm, and then can assume on the data, and then from that we estimated the semivariograms of those data, of transformed data. So, and we additionally assume that this is a wide sense stationary random function with a Gaussian multivariate probability distribution. So it's also strict stationary, and under these assumptions we go ahead and do the simulation. So we want to first simulate a new value at conditional to all these points of this. So we first start with revisiting all those points in a certain order. It can also be randomly. And we start with this one. So the first step is to take a radius of influence, which is equal to the range of the semivariogram, and select all the observation locations that are within that radius. Then we perform a multi-Gaussian kriging, which gives us the probability distribution of Z given the values at the n locations around it. Yeah. So using multi-Gaussian kriging. So this is how it is portrayed mathematically. This is the cumulative probability distribution of Z at this location x0, given the n observations around it. Yeah. Then what we do is we now know the conditional probability distribution here, so we can draw a value from it. Yeah. And that value then is assigned to this grid. Now we go to the next grid point. Suppose that's this one here. Yeah. Now we do again calculate the conditional probability distribution. However, we're not only using the observations, the actual observations that we found, but also all the values of the previous simulated nodes as if they were observations. And why is that? That makes sure that this one is not only conditioned on this, but also on the value that's here, which guarantees that we don't get an independent variable here that's independent of the value there, but that there is a correlation between the two, and that is exactly such that it behaves the correlation structure that is embedded in the semivariogram. So this is why it's called sequential simulation, because we're adding previously simulated nodes as observations. So this is the conditional probability of Z at this new location, given not only the n observations that we have, plus the previously simulated node. Then we draw another value from it, and we go to the next. So every time we visit a new node, we do a multi-Gaussian kriging and draw from the conditional probability distribution, but we do a multi-Gaussian kriging given the observations, the actual observations, and all the previously simulated values treated as observations. Yeah, and by this you get, by construction, a realization at the conditional random function. Now, after all the nodes are visited, you have one realization. And then you can redo it again to get a second realization, and a third and a fourth. Yeah, and because you're randomly drawing, and what often is done to avoid any artifacts, they also randomly visit all the nodes. At each new realization, there's a different order at which the nodes are randomly visited. You get, by this randomness, you get realizations that look more or less the same, but they are not exactly the same. Yeah? And actually, if we would say simulate 1,000 of these and then take for every location the average of those 1,000 realizations, what we would get back is exactly the simple kriging prediction at that location. Yeah. Simple kriging can calculate it directly, but this is how it's calculated. But you can also do it, by simulating many of those realizations and then averaging them. But of course, these realizations are used as input to, for instance, a groundwater model in a Monte Carlo analysis to not only get a prediction of the head, but also the error. You can also estimate the full uncertainty about the model outcome. Yeah? So we get a probability distribution of hydraulic head at every location, or we can get the mean and the variance of that probability distribution at every location. And this allows us to do uncertainty analysis, basically get assess what the uncertainty is in the outcome of the groundwater model, given the uncertainty in our in one of the parameters, in this case hydraulic conductivity.